So hello everyone, in this video we'll be solving another LeetCode problem, and the problem name is divide an array into subarrays with minimum cost part 2. So you are given a 0 indexed array of integer nums of length n and two positive integers k and dist. The cost of an array is the value of its first element. For example, the cost of array 1, 2, 3 is 1 because 1 is the first element, while cost of this array 3, 4, 1 is 3 because 3 is the first element. Now you need to divide nums into k disjoint contiguous subarrays such that the difference between the starting index of the second subarray and the starting index of the kth subarray should be less than or equal to this distance dist. And then they have given what they actually mean in other words and all of that. In the end, you need to return the minimum possible sum of these cost of these subarrays. So what the question is saying that, let's say you are given a nums array something like this. So this is the nums array, and let's say the k value given is 4 and dist is any value you can take from your side. We are just trying to understand the question. So for now, don't care about this value. We just want to understand what the question is saying. So let's say k value is 4. So let's say we divided this array into 4 subarrays. So one subarray is this, second subarray is this. Let's say this is the third subarray and this is the last kth subarray. Now we need to make these divisions such that the second subarray's first element index, let's say it is I, and kth subarray's first element index, let's say it is j. The difference between them, j minus I, should be less than or equal to this distance dist. So this is what the question is saying. So you need to make partitions such that this condition should be followed, and also the cost of this subarray, whatever their cost is, it will have some cost C1, it will have some cost C2, it will have some cost C3, and it will have some cost C4. The sum of these costs should be as minimum as possible while taking care of this condition. So this is what the question is saying. Now it is different from the part 1 of this particular problem, because in that we don't have this restrictions of dist, and also there the k value was fixed 3, and k value is also not actually the problem. So how it is different from the part 1, and can we apply the part 1 logic here also? Let us see. So in the part 1 we have seen that this cost 1 value will be fixed, obviously, because wherever you do the partition, the first subarray will always contain this element. So this value will be fixed. We need to only focus on the remaining k minus 1 values that we want to make. Now in this we can't apply the logic, okay, from the remaining part let us get the minimum k minus 1 value. No, it will fail, because here we have this additional constraint that the index difference of this second array's first element and the kth subarray's first element's index should be, the difference should be less than equal to this dist. So here this logic will fail. So how we can solve this problem? So let us see with the help of one example. So this is the example where k value is 4 and distance value is given as 5. Now till now we are clear that, okay, this value will always be in our answer. This particular 0th element will always be in our answer, because wherever you make the first cut, the first subarray will always have this value inside that subarray. So obviously this 0th index will always be in our answer. Now we need to take care about the only k minus 1 values. So k minus 1 values will be 3. So we need to take 3 minimum values. Now we don't have to take these 3 minimum value from this entire remaining part. No, we need to make sure that distance condition should also be possible. So where do we need to find this k minus 1 value? We need to find the k minus 1 value within this range, from this 1 up till this 6, because we cannot have the distance between the j minus I to be greater than this distance. No, we don't want that. We want that j minus I should be less than equal to distance. So we can at most take the difference to be distance. We cannot take more than the distance value. So we can at least have the separation between the j and I to be distance, not more than that. Less than that is okay, because that is in our condition. So this can be the maximum boundary or value we can reach out to. So within this boundary we need to find the k minus 1 minimum values. So you can see this is the 6th index and this is the first index. So j is actually 6 and I is actually 1, and if you take the difference 6 minus 1, that is equal to 5, which is less than equal to 5, or rather it is equal to 5. So we are within these conditions, and now from here we need to take the k minus 1 minimum values. So this is the logic, but this is the only boundary, or it is the only part which will have the difference of the distance to be 5. No, we can also have this particular part from 2 to 7 whose difference is 5. We can also have this distance, this part whose difference is 5, 8 minus 3. So from here what you can see, it is a kind of sliding window. So let me just show you what I am saying. So what I am saying, that first we are checking in this particular part for the minimum k minus 1 values, because it has the distance of 5. Now it is not the only part where we need to check, because you can see from 2 to 7 also the distance is 5. So we can check k minus 1 minimum values from here also. From 3 to 8 also the distance is 5. So we can take k minus 1 minimum value from here also. So within these all the cases, whatever are the minimum actual k minus 1 values, we need to take care of that. So we need to do this efficiently. So from this particular drawing explanation, what do you understand? What is this happening? This is actually a sliding window. So we can check for this window what are the k minus 1 minimum values, then we can add this element and remove this element. Then we can check within this particular boundary what are the k minimum values, then we can add this element and we can remove this element, and so on and so forth. We can check for every window whose size is distance plus 1, because if you have the window size distance plus 1, then only the last element and first element's difference will be equal to distance, right? Then only we will get the difference to be distance. So we need to check each and every window of size distance plus 1. So from here we get the idea, okay, we need to use the sliding window technique. Sliding window. Now this was not actually a tricky part. This thing was like if you draw some scenarios on the first example or second example, you would be able to come up with this logic very easily. This is not the main part. The main part is that how will we get the minimum k minus 1 values, because what comes to your mind when you think of minimum values? Either set comes to your mind or min heap come to your mind. In my case, I was thinking about the set, or rather I would say multi-set, because we need to take care of the duplicates also. So I thought, okay, let us use multi-set, and in that the values are already in the sorted order. So yes, we can get the k minus 1 first value, and that will be the minimum. But wait, if we just move our window one step ahead, that means we need to remove some elements and we need to add some elements. So that means we don't know like actually at which position this new element will be. So we cannot keep track of which value will be added, whether that particular value will be included in our k minus 1 minimum value or not. So for that we need to iterate this entire set, but that is not efficient. So from here I thought, how can we solve this using set, or how can we solve this using priority queue? So with one set I wasn't able to come up with the solution. So I looked at one of the hint, I think it was hint 3, which says that you should use two priority queues. Now in my case I wasn't using priority queues, but I got the hint, okay, with one multiset I cannot do the approach, so why not try to use two multiset? Now how you can use two multiset? You can store one multiset with only k minus 1 minimum values. One multiset will only take care of the k minus 1 minimum values, and the other multiset will take care of the remaining elements. So first multiset will take care of the only k minus 1 minimum values. So whether we are adding something to it or removing something to it, we will able to easily know whether our current sum, obviously we will take care of the current sum also, what is the sum of the minimum k minus 1 values. So whether we are removing something from this set or we are adding something to this set, we will easily able to know. And if we are removing, we can easily decrease that particular value from our current sum, and if we are adding something, we can simply add that particular value to our current sum if we are adding to this particular multiset, because this will only keep track of the k minus 1 minimum values, right? So if you didn't understand, let me show you with the help of one example. So this is the scenario we are taking. We are keeping two multiset, which one will be always taking care of the k minus 1 smallest elements, and other multiset will be taking care of the remaining elements which are not minimum k minus 1. So what I am saying, that if we have this one multiset which will always take care of the k minus 1 minimum values, then whether we are adding something to it or removing something to it, we don't need to iterate over this entire multiset to compute the sum, because whatever element we are removing, we will know, okay, so this is the element we removed. So from the current sum that we are keeping, we can just subtract that value, and if we are adding something to it, we can just add that particular value to our current sum, because this will only keep track of the k minus 1 element. Its size will be always k minus 1, so we don't need to iterate this entire multiset again and again. That's why we keep two multisets. In one multiset we need to do the iteration again and again to find what all are the minimum k minus 1 value, but this set is itself taking care of the k minus 1 values, so we don't need to iterate again and again. So let me show you how these operations will be done. So we now know that, okay, we need two multisets. We now know that we need two multisets, but how will we take care of the elements, the flow of the elements? Which element will go to the smallest multiset, or which element will go to the remaining multiset, this multiset or this multiset? In which part this element will go, which multiset this element will go, we don't know. So if we move our window, so this was the first window, let's say we move our window to here, that means this element will be removed and this element will be added. So we don't know where this element will be added and from where this element will be removed, so that we will see now. So let us see that. So let's say the k value is 4, so that means the k minus 1 value is 3. So we need to keep track in the multiset the 3 minimum elements. So let's say the current scenario is these 3 elements as the minimum elements. So now we move our window to here. That means this particular element will be added and this element will be removed. Now first of all, let us say how will we add this particular element. Let's say that element is 3, or rather forget about the 3. Let's say that particular element is 5. Now if this element is 5, not take care about the 3 right now, let's say this element is 5, this particular element is 5. Now we know that the largest value in this smallest multiset is 4 and the current value is 5, then obviously this 5 cannot enter into the smallest multiset, because these 3 will be surely the minimum. That means we need to put this 5 into this multiset, that is the remaining multiset. So we will put this 5. So this is the simple case. So if the last value of the smallest multiset is lesser than the current value, that means that current value will be added in the remaining multiset. But what if there is some other scenario? Let me show you what is that other scenario. So let's say this is the other scenario where you have this element as 3. So let's say this element as 3. Now you see the last element of the smallest multiset, this is 4, and it is greater than this 3. That means what? This 4 should be removed from this multiset and this 3 should be added in the multiset. So this 3 will be added in the multiset and this 4 should be removed from this multiset, and this 4 should be going into this multiset. So this is what we will do when we need to add an element. So add an element has two types of scenarios. If that particular value is lesser than the last value of the smallest array or smallest multiset, that means that last value should be going into the remaining part and the current value should be going into the smallest part. And if that current value is larger than the last value, then obviously it will be going into the remaining part. So this is for the add operation. And what is for the remove operation? So let us see what will happen in the remove operation. And yeah, side by side we will be adding and subtracting from our current sum also, because this current sum will keep track of the sum of the k minus 1 values. So whether we are adding some value to the smallest or we are removing some value from the smallest multiset, we will add or subtract from this current sum also. So keep in mind that we are doing this operation in this part also. So whatever operation we are doing in the smallest part, that will be applicable to the current sum also. So just keep that in mind. So now let us see for the remove part. So remove part also has two types of scenarios. So let's say the removed element is 5. So let's say the last element, when we shift the window, this element was 5. So that means we need to remove this 5. Now first we will check in which multiset this 5 value is present. If it is present in the remaining multiset, yes, it is present in the remaining multiset. That means we don't need to do anything with the current sum and the smallest multiset. Everything will be remaining same. We just need to remove this 5 from our remaining multiset, and remaining multiset has nothing to do with the current sum. So everything will work smoothly. But what if there was some other scenario? Instead of 5, the element we are trying to remove is 4. Now this 4 is present in the smallest multiset. Now this 4 is present in the smallest multiset. So if we remove the 4 from the smallest multiset, we need to remove it from the current sum also, or we need to subtract it from the current sum also. So okay, we remove this 4 from the smallest multiset. But here you see there is one problem. Now there are not 3 elements present inside this smallest multiset. We need to have k minus 1, or we need to have 3 elements inside this smallest multiset. So what we can do? We will pick the value which is smallest in the remaining multiset, right? So from the remaining multiset, whatever is the smallest value, we will pick and put it into our smallest multiset, such that it will hold the property of keeping k minus 1 smallest element. So we removed this 4 from the smallest part, so we subtracted from our current sum. Now we are adding this 5 into our smallest multiset, so we will add that 5 to our current sum. So this is what is happening in the add part and the remove part. So I hope you understand this particular scenario, and this is it. We got the sliding window logic. We will check each and every window of size distance plus 1, and within that distance, or within this window, what all minimum k minus 1 values are there, we will be solving that particular part with the help of this multiset approach, or rather two-multiset approach. We'll be keeping two-multiset, right? So this is the problem. So let me show you code so that you can understand in more better way. So this is the code. So first of all, I have declared a variable n, which is nothing but the size of the nums array. Then I have declared a variable answer, which will keep track of the minimum cost that we can get. And now what we need to do, we need to apply the sliding window, right? Sliding window with the window size of distance plus 1. So first we need to keep track of the first window, then we can slide. So for the first window, we are just doing the iteration from I equal to 1, because I equal to 0 will be always included in our answer. So for the k minus 1 values, we will start the window from I equal to 1 up till I is less than equal to distance plus 1. And we are keep on adding elements to our respective multiset. So let me just show you. So these are the two multisets that I have created. Smallest element multiset, which will keep track of the k minus 1 minimum elements, and the remaining elements multiset, which will keep track of the values that are not minimum k minus 1. So I will also tell you what is this add element function doing, but for now you can just understand that for the first window, we are just adding this nums of I value to either of the multiset, either to the smallest element multiset or to the remaining element multiset. So you can just think it of for now like this. And now whatever will be the minimum k minus 1 values, we will keep track of their sum in the variable current sum. So while we call this add element function, we will keep track of the current sum also. So for the first k minus 1 minimum elements, we are just assigning the current sum to our current answer, and then we will try to minimize this answer as minimum as possible. So we are checking for the other windows. Now the window will start from distance plus 2, obviously, because distance plus 1 we have already done. So I will be starting from distance plus 2, and it will go up to less than n. Now what we will do, if we are at this window and we are going on to this particular window, that means we will add one element and we will remove this element. So we are adding this value nums of I, and we are removing this value nums of I minus distance minus 1, and we are also giving the k value. Now we will see what will happen in this add element function and the remove element function. So let us see about the add element first. So add element, obviously if the smallest element is already less than k minus 1 size, that means we need to insert all the values inside the smallest element array. This is the base case. So I haven't explained in the drawing explanation part because this was obvious. If the smallest element size is itself not k minus 1, then obviously we will insert them in the smallest element multiset. And also we will just add those value to our current sum. Otherwise, if the smallest element size is not less than k minus 1, then what we will do? We will have two scenarios. We have discussed two scenarios. Either the current value will be larger than the last value of the smallest multiset, then obviously we will push this current value into our remaining element multiset. Otherwise, if this current value is lesser than this last element of the smallest multiset, that means we need to remove this last value and insert this 3 into our smallest element multiset. So this is what we are checking. If the current value is less than the last element, so we have computed the last element of the smallest element multiset. If this current value is lesser than the last value of the smallest element multiset, that means we need to remove this value from the smallest element multiset. So we are removing this element from the smallest element multiset and we are inserting into the remaining element multiset. And if we are removing it from the smallest element multiset, that means we need to subtract it from our current sum also. So we are subtracted in from our current sum also. And now we need to add this 3 or whatever this value is to our smallest element multiset. So we are just inserting that particular value into our smallest element multiset. And if we are inserting some value into our smallest element multiset, that means we need to add that particular value to our current sum also. So we are doing that only. We are just adding that particular value to our current sum also. So this was about the add element part. Now what we will do if we need to remove an element. So remove element also has two scenarios. Whatever value we are removing, either that is present in the remaining element multiset or the smallest element multiset. So if we are removing the element from the remaining element multiset, that means it is okay, just remove it because it doesn't need to do anything with the current sum. Current sum has to do only with the smallest element multiset. But what if we are removing that particular element from the smallest element multiset? So we will check. If this particular value is present in the smallest element multiset, that means we need to remove it from the smallest element multiset. So we are just erasing it. And if we are erasing it, that means we need to subtract it from the current sum also. Now we know that okay, we removed one value from the k minus 1 multiset. So it is no more having k minus 1 elements. It is having k minus 2 elements. That means now we need to add the minimum value that is present in the remaining element multiset to this smallest element multiset. So we are taking the minimum element from the remaining element multiset, we are taking that element and we are adding it to the smallest element multiset. And if we are adding something, we need to add it to our current sum also. And obviously if we are adding this particular value to the smallest element multiset, we will be removing it from the remaining element multiset. So we are just erasing it from the remaining element multiset. So this is what we are doing. So it will keep on doing for each and every window of size distance plus 1, and whatever gives us the minimum k minus 1 sum, we will just take that and add it with the first value, because this first value will always be in our answer. So whatever answer we get the minimum, we just add with the first value and we will return that. This will be the minimum possible cost that we can get. So I hope you understand this particular solution. I have tried my best to explain this. If you have any doubts, you can write in the comment section. I'll be answering that comments as soon as possible. So if you have any doubts, you can write in the comments. So yeah, I hope you understand this particular solution. Thank you for watching.